science. And then there's a few other minor points to finish off this chapter. So given that, I'll be reviewing quickly the Euclidean algorithm. Any other questions or any other points? Everybody happy? So remember, to support your work in this course, just to reiterate, you really need to be all those tutorial exercises in the book. I mean, in the fortnightly number theory tutorials, we certainly won't get through all of them. I'm doing some of them in the lectures as well, but you are encouraged. I do expect you to be working on all the problems there. As we go through, I'll be releasing solutions as we go through. We should probably release the solutions in the first chapter anyway. Now, pretty soon I'll release the solutions from the second chapter after this week, I think. We should be aiming to get complete coverage of all those exercises to help you with the tutorial. Okay then. So to do the quick review, this begins by looking at the definition of the greatest common divisor. We saw that a few lectures ago. Okay, the greatest common divisor of a pair of numbers is, as the title says, it's the largest number that's dividing both of the numbers, A and B. Okay? And this is important. It measures the kind of relationship of the two integers to one another, and you'll see its importance come up, as we go through the course. A particularly interesting case is when we've got a pair of numbers which have a greatest common divisor of 1. Of course, 1 is always a common divisor of any pair because 1 divides everything. You'll remember from chapter 2. So 1 is always there as a common divisor, and when it is the greatest one, in effect the only divisor, well, 1 and minus 1 would be divisors, but essentially 1 is the only divisor. That's special, and we call those pair of numbers a co-prime pair. And it will turn out that means that the numbers share no prime factors at all. Let's see. Okay, so we have this challenge of how do we calculate greatest common divisors. It's easy enough with small numbers. You can figure it out quickly. You can identify all of the small numbers divisors, but it's a very hard problem given an arbitrary large number. There aren't really efficient ways for finding all its factors, but there is efficient ways to working out the greatest common divisor of a given pair of numbers, and that's thanks to this algorithm we have called Euclid's algorithm. So if you fast forward to page 13, we see the operation of the algorithm here at the top. So this problem here on page 13 is trying to find the greatest common divisor of these two numbers, 12378, 12,378, and 3054. And remember, it proceeds by doing a sequence of integer divisions with remainder. Okay? So we divide the A by the B. It goes in a certain number of times, and you're left with a remainder. Okay? That's quite a quick operation to do, even with large numbers. Okay? And we then, you can see the pattern, we then take the number that we divided by, and we take the remainder, and that's our new input pair. We divide the number we just divided by, we divide it by the remainder. We get a new quotient and a new remainder, and the process continues, dividing 162 by 138 and so on. Now why are we doing this sequence of integer divisions with remainder? Well, there's a lemma at the top of page 12, but they're all examples of this kind of thing, doing integer division with remainder, a equals bq plus r, and the lemma 2.4, which is really the proof that the Euclidean algorithm works and does what it does. Lemma 2.4 said that the GCD of A and B, if we have this relationship, the GCD of A and B is equal to the GCD of B and R. Okay? So, although we're doing different integer divisions, What's always true throughout all of these is that the GCD of the original pair, 12,378 and 3,054, the GCD of that pair is equal to the GCD of each kind of input pair all the way down. Now these integer divisions with remainder, the point about them is that the remainder that comes out has this nice property, that the remainder is always strictly smaller than the divisor when you did the integer division with remainder. So you do the first one, you get a smallish remainder r, smaller than one of the input pair. Then when you do the second one, second integer division, you're going to be dividing by r. So the new remainder you get is going to be smaller than this. So you get a descending chain, a descending sequence of non-negative numbers. And where must a descending sequence of non-negative numbers end? There's a point that a descending sequence of non-negative numbers can't get past, and that's the point 0. And no matter where it starts from, it has to bump into the wall of 0 after a finite number of steps. Okay? We see it here. After a few integer divisions, we reach 0 here. And the point is, because the GCD is preserved all the way along, in this example, when you look at the final equation, what you're saying is that the GCD, this is equal to the GCD of 6 and 0. Okay. Now we don't have to think about what the answer to that question is, because the GCD of anything non-zero with 0 is just equal to whatever the other value is, right? So this is equal to 6. The GCDs have been preserved. They're the same all the way down. So 6 is GCD of the original input pair. So how it's normally said is that you have the sequence of integer divisions, and the last non-zero remainder is the GCD. So I've got a little underline there. But the last non-zero remainder, it's the same as this number here, the GCD of 6 and 0, 0, to the GCD of 6. Okay? So that's the output of the greatest common divisor. The output of the Euclidean algorithm, sorry. But the Euclidean algorithm also gives you a second thing. It gives you what we've been calling Bezout's identity, which is a linear combination of the original input pair that is equal to the greatest common divisor. Okay? That will be a very useful device for us as we go through number theory. And it uses the same to obtain that linear combination. We use the same set of equations, but we just work backwards. So the second last one gives us a linear combination for 6 as a linear combination of 24 and 18. But then we get another linear combination for 18 as a linear combination of the next up pair. So we can use that to replace 18 in this one. And you keep doing this substitution procedure until finally you end up with 6 expressed as some linear combination of 12,378 and 3,054. You can see that process begun here. We do the first few steps of it, and then we're just saying, just keep going. Then at the end, you see the coefficients come out as 132 minus 535. So that's the Euclidean algorithm, giving us the GCD and giving us the linear combination of the original two inputs that's equal to the GCD. Now, it's laid out here in the form of a formal result, algorithm 2.1, the Euclidean algorithm. It's basically just repeating what's going on in that example there, but just in a general formal way. So we set up some kind of sequence of integer divisions and just kind of just giving a consistent labeling of the original input pair A and B. But then as you go to the middle, really what you're doing is you're doing these integer divisions with remainders, with sequences of remainders that have come from earlier divisions. And eventually you get clean divisibility. You end up with a remainder of 0 down here. So the GCD is this number, Rn. And then it just talks a little bit formally about how you do the reverse substitution process to get the required linear combination. And normally a specification of an algorithm there would have a proof of why it's justified to call it an algorithm. Remember, if you want to call something an algorithm, it has to be two things. It has to be completely unambiguous in its specification so that you can easily translate it into a computer program. But secondly, we normally only use the word algorithm for processes that are guaranteed to hold. Okay? Because there are certain computational methods or computational enterprises you might embark on, but sometimes they're such that there's no guarantee the process will ever end, or but this is certainly not that case. And the justification for that is basically considering this inequality that the remainder has to satisfy. The remainders are always non-negative, but they're always less than the previous remainder. So that forces them to be a descending sequence of things that's running up against the hard wall of 0. So eventually it's going to stop. Okay. And there's a sequence of integers. You can obviously have infinite descending sequences of rational numbers, or real numbers, fractional quantities getting ever smaller. Those sequences don't have to end. Those can be infinite descending sequences. But descending sequences of integers, of non-negative integers, have to end. They have to be finite. Okay. Any questions on the Euclidean algorithm from your work on it during the week? So it's an algorithm. The whole point is we can program the computer and get the computer to tell us the answers. But it is worth doing it by hand enough times so that you're familiar with how it works. Okay. The exercise is 2.2 here. There's just some. I mean, these are just random pairs of numbers off the top of my head. But you should be able to sit down and perform the Euclidean algorithm for reasonable sized inputs, and just do it correctly, and just to ensure that you understand the specification of it and how it works. Okay. Now I'll do some of these. Obviously this week, at the end of this week, we'll be looking at all of the exercises at the end of chapter 2. I may get time to do one or two of them now. But just a few things to look at the end of chapter 2. We get this nice result, which we can also get just by carefully considering the operation of the algorithm. So this is a result which tells us something about how the greatest common divisor behaves as a function. And it says that the GCD of MA and MB, what's going on there is the input pair we're giving it has this common factor already. Okay. So the two numbers that you're putting into GCD, if you know they share a common factor already, here of M, then that M can be factorized outside the GCD. Okay. So the GCD of MA and MB will be M times the GCD of A. Don't be tempted to take it out twice and say it's M squared. It just comes out once. Now the proof of that, well, you might prove that a number of different ways, but one way of proving it is we can just look at how the Euclidean algorithm is operating. We say this follows immediately from observing the sequence of integer divisions in the algorithm, and just noticing this equivalence here, that at every stage, whatever integer division you're doing here to carry out the GCD on the right-hand side, so for instance, you'll be dividing A by B, you'll get a quotient Q1 and a remainder R1. If you look at the same integer division for the quantity on the left-hand side, there you'll be trying to divide MA by MB. Well, we're just noticing that it's exactly the same quotient, Q1, that occurs here, and exactly the same remainder after multiplication by M that occurs over here. Okay? So the quotient and remainder here are exactly the same as the ones over there. Okay? So basically, the sequence of integer divisions that you need to carry out the Euclidean algorithm on the left-hand side, you can get those by taking the sequence of integer divisions for the GCD on the right-hand side and just multiplying each one across by M. Multiplying both sides of each one by M, and that will just be the Euclidean algorithm for the right-hand side. Okay. So that's basically all we need for that. So the final remainder that comes out for the calculation of the GCD AB, that will be some number Rn, the final non-zero remainder that you hit in the Euclidean algorithm. And the GCD here, well, because we have this mirroring of the two sets of equations, the final non-zero remainder will be M times Rn. okay, which is the required result. Any questions about that? There are, when you look at the exercises at the end of the chapter, see on page 16, you know, there's a few other similar looking-ish properties of the GCD. Ways the GCD function behaves on certain kinds of inputs and relationships that it has. So some of those might be proved either by reference to how the Euclidean algorithm is operating in those cases, or by using just the original definition of the GCD. So, any questions at that point? Anybody got anything about the Euclidean algorithm that you'd like me to clarify or say something about? I also want to show you, today, but I also want to show you how easy it is to actually write the computer program that will carry that out. And I'll hopefully show you that in MATLAB and in Sage, writing it in Python as well. So we might do that next week, or might even do that in the tutorials into this week. You can write it in more or less just 4 or 5 lines. That's what you do. Okay. So if there's no questions on it, then we'll just deal with these last few points in this chapter. We've got a quite closely related concept here, the least common multiple. You may have heard of this before. So it very much kind of mirrors, in some sense, the greatest common divisor. So you've got the greatest common divisor and the least common multiple. Kind of looking at the same kind of concept from the other side, if you like. So what's the least common multiple? Again, it's attached to a pair of inputs. So the least common multiple of a pair of inputs, well, it is what it says it is. It's the smallest positive integer that is both a multiple of A and a multiple of B. So typically, we're expecting it to be larger in absolute value than A and B. Although, if A is already a multiple of B, then the smallest common multiple of A and B will be A itself. So let's just throw down a few examples of this before we look at the theory of how it's related to the GCD. So, oops. Okay, some really baby examples. The least common multiple of 2 and 3. It's the smallest integer. There's both a multiple of those. 6. Yeah. Smallest number that's a multiple of 2 and 3. I guess we're saying smallest positive number. Smallest positive integer, yeah. Least common multiple of 6 and 15. Right. You get the idea. Now, we'll be able to understand this quite well once we know about, or once we have the fundamental theorem of arithmetic about it. The fact that everything factorizes uniquely into products of primes. So these are the prime factorizations of 6 and 15. You can understand, just as you can understand the greatest common divisor as whatever overlap there is in the 2 factorizations. So here you see an overlap of 3. 3 is the only part that's common to both factorizations. So 3 is the GCD of 6 and 15. But you can also understand the LCM in terms of the prime factorizations. It's basically the minimal, basically the union of the 2. So the GCD is the intersection of the 2. The LCM is the union of the 2. So we have to include a 2. We have to include a 3. We've already included a 3, but we have to include a 5. So that's how the least common multiple works in terms of prime factorizations. But formally, where we stand at the moment, we haven't yet proved that theorem, that every integer has a unique prime factorization. That's to come fairly soon in chapter 3. We're going to be using the greatest common divisor idea to prove it. But we're not quite there yet. Okay, so that's the least common multiple. But again, you're kind of hit with if you have some gigantic pair of numbers, what's their least common multiple? Well, how would you? I mean, this approach of using prime factorizations again isn't kind of a good, effective way to work, because finding prime factorizations for very large numbers is hard. Computation is hard, but we can calculate these least common multiples in a quite straightforward way, because the least common multiple is kind of chained to the greatest common divisor. They aren't really two independent things. They're kind of locked together in a certain relation, and this is this theorem 2.6. The 2.6 says, well, you got a pair AB, the GCD and the LCM, they're locked together because when you multiply them together, that has to be equal to the product of the two integers, A times B. Okay. We can observe that here. So the GCD of 6 and 15 is 3, as we observe. So the LCM times the GCD is 30 by 3, which is 90, and of course that is equal to the product of the original input pair, 6 and 15. So it checks out with that example, and it isn't just a fluke, it's true in general. Okay, and here's a proof, which they could prove this in terms of the prime factorizations idea, in terms of the overlap and union of prime factorizations, and that would be a good exercise to do, except that it's all premised on we need to prove the fundamental theorem of arithmetic first. Okay? But here is a proof which just deals with the linear combinations idea, I think, yeah, which we already have about the greatest common divisor. So here's the proof that it is always true that when you multiply the GCD and the LCM, you get the product of the original pair. So the way we're going to prove this is we're going to let D be the GCD of A and B. And the way we're going to do it is prove that when you divide the product AB by D, so when you divide the product by the GCD, you get exactly the least common multiple. So if you want to prove that a certain quantity is equal to the least common multiple, you have to prove two things. You have to prove, first of all, that it is a common multiple. It has to qualify as a common multiple. And then you might go and tackle proving the idea that it's the smallest positive common multiple, the least. So first of all, we take care of showing that AB over D is a common multiple. Okay. Well, now this number D is special. It's a common divisor of A and B. So we can write A as some multiple of D and B as some multiple of D. All these quantities are integers. So A is an integer multiple of D, as is B. So when you perform the fraction AB over D, there's a couple of ways of writing that. You can either write it as, well, you see, A times B will be alpha beta D squared. So when you divide it by D, you'll have alpha beta D, alpha beta D. And that alpha beta D can either be expressed as alpha times B, if you take the beta and the D to be B, or you can express it as beta times A. Take the alpha and the D to be A. Okay. So here, you're looking at this quantity AB over D, and it's clearly a multiple of B, and it's clearly a multiple of A. So it is a common multiple. Okay. A number that's a multiple of both the input pairs. So that AB over D, well, A is a multiple of D, B is a multiple of D, so it becomes alpha beta over alpha beta D. It becomes alpha beta D. And it's just a case of whether you regard the alpha times D as being A or the beta times D as being B. That gets you those two expressions. Everybody okay with that? So that establishes that it's a common multiple. Now we just have to worry about it being the least common multiple. Well, the way we prove that is we take any other common multiple at all, C. So we take into our picture a general common multiple, C of A and B, then our task will be to show that this number, we're trying to show the LCM, we want to show that that is less than C. So in that way, if we show that it's less than any other common multiple, then it has to be the least common multiple. So how do we do that? Well, the property that this number C has is that it's a common multiple of A and B. So I just want to name the associated factors. So I say C is equal to a lambda times A, and C is also equal to a mu times B. So C is a common multiple. And then I bring in, here is where the proof has to rely on the linear combination idea associated to greatest common divisors. Okay. So calling back to this number D, this number, see, we've only used the property of D is that it's a common divisor. Here is where we actually make use of the fact that it's the greatest common divisor. Greatest common divisor is special because it can always be written as a linear combination of A and B. It's the only common divisor, except for negative D, which is trivially true by just multiplying both sides by minus sign. It's the only common divisor that can be expressed as a linear combination of A and B, the greatest common divisor. All other common divisors cannot be expressed as a linear combination of A and B, except for minus D. So there's the greatest common divisor expressed as some linear combination of A and B. So I know the M and N exist. Now I'm trying to prove that AB over D is smaller than C. And the way I'm going to show that is that it divides C. So now I say we examine the quantity C divided by the integer AB over D. We already know AB over D is an integer. It's equal to alpha beta D, AD or BD. Sorry, alpha D or beta D. So AB over D is an integer. Now I'm looking at C divided by it. So my task here is to show that, excuse me, that this is an integer. Okay. Obviously, it's a rational number automatically, so it's a fraction of integers. If you take the D above the line, it becomes CD over AB. But if I can show that that's an integer, then I'll have shown that AB over D divides C, in the sense of our definition at the beginning of chapter 2. And if AB over D, it's a positive number. If it divides C, then it has to be smaller than C. So that will show that it's the least common multiple. So it's smaller than every other one. So here's my CD over AB. And here's where I bring in the linear combination for D. So this only exists, this linear combination of A and B, this only exists because D is the greatest common divisor. So we've got CMA plus CNB. So I can split that up then, because in the first part I can cancel A's, and in the second part I can cancel B's. So I get C over B times N plus C over A times N. Now those numbers C over B and C over A, those are special. Those aren't just rational numbers. I know that they're integers. Why? Because the number C is a common multiple of A and B. So I've already introduced the lambda and mu, which are the associated factors. So C over B is mu, C over A is lambda. Those are integers that were introduced a few lines ago. So I see here I've just got a linear combination of integers. Integer times integer plus integer times integer. So it is indeed an integer. So we've been able to show that this quantity on the left, which originally just appeared as maybe some rational number, but I wanted to show it was an integer, to show that this thing does indeed divide C. And we were able to show it's an integer. Of course, and it relies on the existence of M and N, which are the coefficients in the linear combination that gives you D, the greatest common divisor of A and B. And it also relies on mu and lambda, which are the associated factors in C, for C being a multiple of A and a multiple of B. So it's all the ingredients there, all the conditions, all combined together to get us the result we want. So we've shown there that AB divides C, so in other words, AB over D is no greater than C. So therefore, it is the least common multiple because it's smaller than every other common multiple. So that establishes this result for us, that the least common multiple of A and B times the GCD of A and B, they aren't two independent kind of varying quantities. They are really just two expressions of the same underlying concept, because when you multiply them together, that's fixed to be the product of the input pair. If you know the GCD, you know the LCM and vice versa. Any questions about that? Okay, so I'll be seeing you on Friday for tutorial. We've got a whole bunch of questions there at the end of chapter 2. I won't forge ahead now into chapter 3. We'll start that next week. But we will get going on some of these exercises. So first of all, in exercises 2.2, would you like me to do an example of the Euclidean algorithm for you? I'm seeing some heads nodding. Okay. I'll do one quick example. I kind of hesitate to spend ages doing them in front of you because it's potentially, it's not something I'm great at, spotting all these integer arithmetic. Actually, when it comes to real numbers, I can be a bit clumsy. And it's not something I don't think that's hard to understand in a sense. It's just there's a certain specification to the algorithm. You just got to do it, following the instructions carefully, just so you get a feel for it. So you kind of understand it, right? So let's take one of these examples. I won't take the one with the biggest numbers. I'll go 1, 3, 8, and 24. Not too big, not too small. So this is exercises 2.2, question 2b. With the GCD of 24 and 138. Okay. Okay, these numbers are huge. I don't know what the prime factorizations are. We'll pretend that. So how do I work out the GCD? Well, I start doing my integer divisions. Okay. Start the integer divisions. So I'm attempting to divide 138 by 24. So 4 times 24 is just under 100. So 5 times 24 will just be over. So we'll probably go in 5 times, won't it? So 120 plus the remainder of 18. Okay. Remember, the remainder you get out must be strictly smaller than the number you just divided by. Because if it isn't, if it is a bigger number than 24, well then you can take another multiple of 24 out of it. So that's what we're doing. We're taking multiples of 24 out of 138 until we're left with something that we can't take anymore. Now we'll also put down here the associated GCD equation. This tells me that the GCD of 138 and 24 is equal to the GCD of 24 and 18. That's what the lemma 2.4, I believe, was numbered. So next we take 24 and we attempt to divide it by 18. So it's going to go in once with the remainder of 6. Yeah. And the associated GCD statement is GCD of 2418 is GCD of 18.6. And we attempt to divide 18 by 6. That's 3. And what's the remainder? 0. Okay, so we've stopped because we've reached a GCD of 0. Let's just put down the associated GCD equation, 6 and 0. Now what is the GCD of 6 and 0? It is obviously 6. It's GCD of anything 0. Anything non-zero and 0 is just the other thing. Or the absolute value of it if it's a negative. So the GCD is 6. And now we can obtain the linear combination. Bezout's identity for this. So we want a linear combination of 6 as something times 138 plus something times 24. That's what we're aiming for. Now we have to start. Okay, it would have been better if maybe I had 4 or 5 integer divisions just to get a real feel for how it's working. So it's maybe quite short. But we start at the second last one. This tells us 6 is 24 minus 18. And then we use this one to replace the 24. So it's minus 18, so it's minus 138 minus 5 times 24. As I say, you don't evaluate these things, and you just go backwards. You collect the terms. I'm not really, I mean, I know all of this is 6. That's no surprise. What I'm interested to find are these coefficients here. So it's a minus 1 times 38 plus 24 and 5 more 24, so it's a 6 times 24. So it's minus 1 plus 6. Okay, the first few times you do it, maybe you might want to annotate your Euclidean algorithm integer divisions like that. Maybe show these numbers sliding to the left. Sometimes people like to do that. But the danger you have to guard against is you have to take the right pair of things to do the next integer division. You don't want to take 24 and start trying to divide it by 5 or something. So it's the smaller of it's the second input pair that you were trying to begin with, and the previous remainder. Sometimes people get all in a flummox about how to order the original pair of numbers. Supposing, really, if this was the A and the B, see, I did a little bit of a trick. I flipped the A and the B. I flipped the order of it. Maybe I should have been going for A equals B cubed plus R as it was originally presented. So notice that if we don't flip, at the beginning, if we do try and divide the small number by the large number, what's going to happen? Just like that. Well, I think I disagree. So how do you divide 24 by 138? Can you divide it and get an integer remainder? I mean, you're right in a sense. You can't divide 24 by 138. But that can't really is the same as saying that the quotient is 0. Yeah. So there are no 138s in 24. So you're forced to say the quotient is 0 and the remainder is 24. Now that's fine. That satisfies the criteria for an integer division remainder, because we've got an A equals Q times B plus R. And the condition on the remainder had to be smaller than the number B, which it is. And then when you slide them across, then it becomes what we originally did. 138 equals something times 24 plus what remainder. So if you are given an input pair where the first one is smaller than the second one, yeah, you can immediately just flip it. So the first genuine, the first interesting integer division with remainder is this one, 138 divided by 24. But formally, and this would make a difference for the computer doing it algorithmically, it's okay. The process still makes sense. So we can do a first integer division dividing 24 by 138. Just get a quotient of 0 and a remainder, just the same input number. Okay. Okay. Any questions about that? Okay. So just do it enough times so that you understand it, and then never do it again in your life. That may be an exam. Always use a computer then from that point on. Now in exercises 2.3, we've done a selection of those already on these induction proofs. But we skipped over these questions here, for instance, this one in question 3. So exercises 2.3, question 3. This was one that's based on just integer division with remainder. So we want to show for all integers a and z that 4 does not divide a squared plus 2. So how might you prove this? It's kind of awkward to try and prove directly, because you're trying to prove a negative thing. I mean, if the task was to prove that 4 did divide a squared plus 2, then we could try and attack that directly, because we'd have to try and factorize a squared plus 2 and show that one of the factors was 4 or 2 squared. But here you're trying to show a negative. So it's maybe a little bit off-putting. But to do this, so this is something based on integer division with remainder. So 4 can never divide 2 greater than the square of something. That's interesting. Well, consider dividing. See, what we can always do is we can always divide the number a by 4. So you'll get a is equal to some quotient times 4 plus a remainder. See, the other difficult thing about this task is we have to show it for every integer. There's an infinite number of integers. So it's kind of daunting. Maybe you might use induction to prove it. But another thing that this integer division with remainder process does, and we'll make a lot of this later on when we look at modular arithmetic, is it splits the infinite set of integers up into a finite number of representatives. Okay, and in this case, when you're dividing by 4, the only possible remainders you get are 0, 1, 2, or 3. Yeah. So we can look at the 4 different cases, because this gives me a finite number of cases. Every integer a fits into one of these 4 cases. So now it's a lot easier to check 4 things than it is to check an infinite number of things. So if r is 0, that implies a squared plus 2 is 16q squared plus 2. And see, that can be divided by 4 as 4 times 4q squared plus 2. And that shows that if you try and divide a squared plus 2 by 4, you get a certain quotient times 4 plus a remainder. So you don't get clean divisibility. So 4 does not divide a squared plus 2 in this case in r equals 0. You can just check all the others as well. If r is 1, then a squared plus 2 is, so you still get 16q squared. You get plus 2q4. So this is 1, so then you get a 1 at the end. I don't really want to write that as 8, because straight away I want to factorize it. You see 4q squared plus 2q plus 1. Again there, the attempt to divide a squared plus 2 by 4, if we wanted to show 4 divided that cleanly, you'd be wanting a remainder of 0. But we don't get a remainder of 0. We get a remainder of 1. Okay. So you can never cleanly divide a squared plus 2 by 4 in the case where the remainder r is 1. You get the idea. We've got two remainders to look at, 2 and 3. So you can just check them in the similar way. In both cases, when r is 2, when r is 3, you'll be able to factorize a squared plus 2, or sorry, you'll be able to express it as some multiple of 4. Now you must be sure that this is an integer here. 4q squared plus 2q is an integer because q is an integer. So some integer multiple of 4 plus, and as long as you have a non-zero remainder here each time, then you don't have divisibility by 4. The idea? So it shows you one way in which this integer division with remainder can be quite useful. We can suddenly prove results about all the integers. So it is never the case that 4 divides 2 greater than a square. And this idea, we'll see this idea splitting up the infinite number of integers into a finite number of possible cases based on, and this number, we'll start to call this number a modulus. This is where modular arithmetic appears, and this gives some clue as to why it's useful and why it's a sensible way to split the integers up. Okay, so I'll see you all again on Friday for the tutorial. Your work to do between now and then is to do as much of those exercises as you can at the end of chapter 2. Okay? Come to the tutorial ready to discuss it. Okay?